Good morning, students. Today we are going to start with the next topic, that is oscillations of a loaded spring. First case is when the spring is placed horizontally. When the spring is placed horizontally, right? In this, we will take a spring and a mass m is attached here. This spring is massless and it is placed on a table, right? Now we know what is its spring constant k, and in the last lecture we have discussed what is the time period formula. It is under the root of m by k, inertia factor divided by spring factor, right? So what is the frequency? It become 1 by 2 pi under the root of k divided by m. This is the directly formula you can see, right? Now the second is when the spring is suspended, when the spring is in vertical direction. When the spring is in vertical direction, right? When the spring is in vertical direction, now how you can explain its motion? This is a spring whose spring constant is k, right? This is figure 1. Now if we apply some weight on it, then what happens? Some extension is produced. I have applied a mass m. Let us suppose it get extend through the length L. It get extend through the length L, right? Now you can say that the restoring force is produced toward this direction. So F1 is equal to, from the condition of simple harmonic motion, F1 is equal to minus K into L, right? In equilibrium, you can say its weight is acting downward. This is figure 1 and this is figure 2. I will draw one figure more for this. F1 plus mg plus is equal to 0 because the spring is in equilibrium position. Spring कौन सी position में? Spring is in equilibrium position. So total upward force must be balanced by the total downward force. F1 plus mg is equal to 0. Therefore F1 equal to minus of m into g. This is equation number 1 and this is equation number 2. Now on comparing 1 and 2, from 1 and 2, you can write minus of KL. This is minus of KL is equal to minus of mg. So what is the value of K become? Mg divided by L. This is the value of spring constant. This is equation number 3. Now I will use the third spring. In this case the spring is in equilibrium. Now if I will further pull it, अगर मैं इसको थोड़ा सा slightly और distance से displace करूँगी, what happens? And it release, then it executes simple harmonic motion. It is L plus y. It is L plus y. The distance through which it get displaced is L plus y. So now what is the restoring force become? F2. And we can write F2 as minus of K into, what is the total extension produced? L plus y. You can mark this as 4. Now what is the net restoring force? If we see these two figure 1 and figure 2, student, in figure 2 it is only extended, or in second it starts executing simple harmonic motion. This is figure 3, right? Here it starts executing simple harmonic motion. Now what is the net restoring force? Net restoring force F is equal to F2 minus of F1. It is minus K into L plus y minus of minus KL. So it become minus of KL minus KY plus K into L. This get cancel out and this become F equal to minus of K into Y. So this proves that it execute simple harmonic motion. This proves this spring execute simple harmonic motion. And what is the expression for its time period? अगर हम time period का expression लिखे 2 pi under the root of m by k, inertia factor divided by spring factor. Put the value of k from this relation, it become 2 pi under the root of m. This is kg divided by L, right? Sorry, mg divided by L. M get cancel out and it become 2 pi under the root of L by g. So the expression for the time period is 2 pi under the root of L by g, and its expression is same as the expression for a simple pendulum. Now the next we have going to start combination of springs. In combination of springs, first is parallel combination. There are two combinations that we have to discuss. First is parallel combination. In parallel combination of springs, the two springs of spring constant, this is a spring constant K1 and the second is having the spring constant as K2. Both are connected through a mass M, right? So in this case, what thing remains same? Because they are connected to the common point. So here the extension produced in both is same. Extension produced is same in both the springs. Same in both springs. तो अब आपके पास यहाँ आ जाएगा, this is F1 is the restoring force here, F2 is the restoring force toward the fixed end. So F1 is equal to minus K1 into Y, F2 equal to minus of K2 into Y. Now what is the total restoring force? F1 plus F2. This is minus of K1 into Y minus of K2 into Y. It becomes minus of K1 plus K2 into Y. So now if you replace, because we want to find the effective spring constant, if you replace these two springs by a single spring which produces the same effect as is produced by these two, तो अगर आप इन दोनों को एक single spring से replace कर दें, whose spring constant is Kp and which produces the same effect as is produced by these two, so F equal to minus of Kp into Y. You can compare it, this is 1, this is 2. From 1 and 2 you can say Kp is equal to K1 plus K2. In parallel combination, the spring constant becomes the sum of the spring constant of individual springs, right? Next is series combination. Series combination of spring. In series combination of springs, you can say there are two springs. One is having the spring constant as K1, second is having the spring constant as K2, and these two are connected to a mass M, right? So now F1 is the, here what thing remains same? Restoring force. Here restoring force in both the spring is same, right? Restoring force is same in both the system. तो अब आप y1 be the extension, but the extension produced is different. That depends upon K1 and K2. Y1 is the extension produced in first spring, Y2 is the extension produced in second spring. So F equal to minus K1 into Y1. So Y1 becomes equal to minus F by K1. Or F equal to minus of K2 into Y2. What is the extension produced? It is minus F by K2. Right, student? Now what is the total extension produced? Y is equal to Y1 plus Y2. Put the value in this relation. This is minus F by, this is minus F by K1 minus F by K2. So you can write this as minus F common, 1 by K1 plus 1 by K2. This become Y equal to minus F. LCM you can take K1 K2. This is K2 plus K1. So you can write this as F equal to minus of, cross multiply करिए K1 into K2 divided by K1 plus K2 into Y. So if you replace these two by, you can mark this as equation number 1. If you replace these two springs by a single spring which produces the same effect as is produced by these two, this is series and here the mass M is suspended. So F is equal to minus Ks into Y. Compare these two equations from 1 and 2. You can say from 1 and 2. Okay, I will start from here next in the next page. This is F equal to from 1 and 2. From 1 and 2. Minus Ks into Y. F equal to minus Ks into Y or F equal to minus of K1 into K2 divided by K1 plus K2 into Y. तो क्या बन जाएगा? Ks is equal to K1 into K2 divided by K1 plus K2. So in series combination you can say Ks is equal to, reciprocal of Ks is equal to 1 upon K1 plus 1 upon K2. राइट. सो ऐसा आपका कौन से कॉम्बिनेशन में आ गया, सीरीज कॉम्बिनेशन में. नाउ द नेक्स्ट इज इफ द मास इज प्लेस्ड इन बिटवीन, द नेक्स्ट केस is case 3. If the mass is placed in between the two springs. अगर हम, ये सीरीज कॉम्बिनेशन हो गया, पैरेलल कॉम्बिनेशन हमने पहले किया. इफ द मास इज प्लेस्ड इन बिटवीन द टू स्प्रिंग्स लाइक इन दिस वे, this is K1 and a mass M is placed here, right? This is K2. Now it is which type of combination? अगर आप स्प्रिंग को यहाँ से उठा के ऊपर ले जाएं, राइट, तो ये कैसा कॉम्बिनेशन बन जाएगा, ये K2 इधर आ जाएगा और K1 ऑलरेडी इधर है, तो इट बिकम अ parallel combination. It is a parallel combination of spring. It is a parallel combination of spring. ठीक है बेटे. तो इसमें क्या रहेगी स्प्रिंग कांस्टेंट, दैट इज के पी इज इक्वल टू K1 प्लस K2. पैरेलल कॉम्बिनेशन में स्प्रिंग कांस्टेंट कितना रहेगा, K1 प्लस K2. नाउ इसमें कुछ हमने स्पेशल केस करने हैं. इफ द स्प्रिंग इज कट इनटू n नंबर ऑफ पार्ट्स, इफ स्प्रिंग इज कट इनटू, अब इसमें एक स्पेशल केस है. If the spring is cut into n number of identical parts, spring is cut into n number of identical parts, what is the spring constant of each part? What is the time period of each spring? ठीक है, तो अभी हमने किया t is equal to 2 pi under the root of m डिवाइड बाय k. अगर आपके पास एक स्प्रिंग है, आपने उसको कितने पार्ट्स में डिवाइड कर दिया, आपकी n नंबर ऑफ पार्ट्स में. कितने पार्ट्स में डिवाइड कर दिया, n नंबर ऑफ पार्ट्स में. तो एक पार्ट की जो स्प्रिंग कांस्टेंट है दैट इज इनवर्सली प्रोपोर्शनल टू इट्स लेंथ. तो आपने एक स्प्रिंग को डिवाइड किया तो k इज 1/l टू द पावर n. तो न्यू स्प्रिंग कांस्टेंट k डैश इज n टाइम्स ऑफ k. k डैश कितना बन जाएगा, n टाइम्स ऑफ k. तो यहाँ से टाइम पीरियड आ जाएगा 2 पाई अंडर द रूट ऑफ m डिवाइड बाय n इंटू k, m बाय n k. सो तो न्यू टाइम पीरियड इज t डैश इज इक्वल टू t डिवाइड बाय रूट n, राइट. ये आपने n नंबर ऑफ आइडेंटिकल पार्ट्स में डिवाइड किया, तो एक्सटेंशन प्रोड्यूस आपकी लेंथ क्या हो गई, l बाय n, राइट. तो ये आपका स्प्रिंग कांस्टेंट कितना हो जाएगा, दिस इज n टाइम्स ऑफ ओरिजिनल वैल्यू. नाउ द सेकेंड केसेस, अगर हम केस 2 की बात करते हैं, केस 2 में हमने ये कहा इफ द लेंथ ऑफ द स्प्रिंग कांस्टेंट k इज मेड n टाइम्स, इफ द लेंथ ऑफ स्प्रिंग becomes n टाइम्स, तो यहाँ पर आपके पास जो k बनेगा, k जो होता है आपका इनवर्सली प्रोपोर्शनल टू 1/l होता है. तो k डैश इज 1/n टाइम्स ऑफ l, राइट. तो ये आपके पास k डैश इज इनवर्सली प्रोपोर्शनल टू k बाय n, इट इज k बाय n. तो t डैश बिकम्स इक्वल टू 2 पाई अंडर द रूट ऑफ m डिवाइड बाय k बाय n. तो जो न्यू टाइम पीरियड बनेगा रूट n टाइम्स ऑफ ओरिजिनल टाइम पीरियड. यहाँ हमने क्या किया, द लेंथ ऑफ द स्प्रिंग बिकम n टाइम्स, यहाँ हमने उसको कट कर दिया. जब आपने इसको n टाइम्स किया तो ये n टाइम्स लेंथ ऑफ स्प्रिंग हो गई n इंटू l, तो इट इज k डिवाइड बाय n एंड इट इज m डिवाइड बाय k बाय n रूट n टाइम्स ऑफ ओरिजिनल टाइम पीरियड. Okay, in the next video I will explain the damped and undamped oscillation. Thank you.